Hi guys, if you do remember in one of my previous video, I showed you how to design a FullAdder in LTSpice. And the FullAdder, if you remember, was made with two AlphaAdder connected with this and an OR gate for the carry. And the AlphaAdder was made with an XOR for the sum and AND for the carry. But the real simulation of this digital circuit is done in VHDL. Now, you can also do in LTSpice, which is also useful as well, but the real thing is done in Quartus or in VHDL, as you prefer. So now we will open the Quartus with a new project wizard, and we will select I don't know, a new folder on the desktop. Let's create a new folder called VHDL AlphaAdder. Let's call it FullAdder instead. And let's use select folder. Name of the project, FullAdder. Next, 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 and then finish. So now let's go to File and let's use a new, and let's create a new VHDL file. We will use the standard IEEE library, so let's use the statement which we can find basically in any VHDL file. I think that this is the easiest way to learn VHDL. Let me open we just import these two lines here. Library IEEE and use IEEE.SDLlogic _1164. So basically the VHDL is done in this way. You first use the entity. The entity is basically the description that you're gonna give at your port. So we will start by defining the AlphaAdder. So the AlphaAdder has basically an input called A and the other input called B, as you remember. This will go inside XOR, and this will define the sum, S, and the other two will go inside the AND, and this define the carry. Now, in the VHDL, the entity is basically what you see outside the box. So you will define the entity as A and B as an input, and these two as outputs. In the entity, you don't care what is inside this box, just what is outside the box. So entity AlphaAdder is and entity. Inside here, we will use the statement port to define what is the input and what is the output. In this case, we will use A and B as a input standard logic, and then of course we will use the sum and C to say the output standard logic. Now the entity is done, and now let's proceed with the architecture. The architecture is written this way: architecture behavior, or architecture RTL, as you want, of AlphaAdder is and architecture. Now, for now, we will just write begin, and now we have to write what is inside this box. So we will write S as XOR B, and C as A and B. So now what we expect here is that when A and B are 1, 0, 0, 1, the sum will be 1, and this is the behavior of the XOR gate, and the carry is 0. And when both of them are 1, sum is 0, and the carry is 1. When all of them are 0, 0, and 0. So this is the AND behavior, and this is the XOR behavior, like this. So now we can just close the program. We can save it, save as, oh sorry, the folder is wrong. Save as, I said the folder was FullAdder. Instead of FullAdder, we will name it AlphaAdder, because we wanted to use the component. In VHDL is, the design in VHDL is done with some blocks called components. Okay, you reuse as many components as you want. So we will make the FullAdder with two AlphaAdder make like this. The sum will go inside the first input, and the cin will go inside the other input. And these two are A and B. And the sum will be here, and the carry will be in OR with this one, as you know from your studies. You will probably do something like this more than use the other way around, because that's how you program in VHDL. So, but before going on, we need to test this guy to see if the AlphaAdder is correct. So let's compile it, because it is not said that it is correct. There are 3 errors. Okay, my bad, because I inverted the two, the dot, and okay. Okay, the design entity FullAdder is undefined. This is not a mistake. It is just basically because I named the hierarchy, top hierarchy, FullAdder, but now I'm designing the AlphaAdder, so it is not wrong. Okay, it is just that I have to say that this guy here is the top level entity for now, and this mistake will go basically away. Now we need to see, after the compilation, we need to make sure that this guy is working. Let's wait a bit. Okay. Okay, I think that the compiling is ended. So let's see if the RTL is correct. Let's go on Let's Viewer and RLT Viewer. We should expect something like this. And there we go. The carry is the end of the two, and the sum is the XOR of the two. Nice. Let's test this guy a bit. So let's go to File, and let's use the New, and let's use University Program VWF. Let's click OK. Let's go into View. Edit, Insert Node or Bus, Node Finder, List, everything to the right, and then click OK. Now we have just to zoom out in the timing that we need. So let's select these two and let's put 1. Now this guy is also to 1 and the other to 0. This guy to 1 and the other to 0. And I don't know, both to 0. Let's run the simulation. Yes. If everything is done correctly, you shouldn't have any mistakes here. So let's zoom in. And we have that when both of them are 1, we have carry 1 and sum 0. When instead I don't know why there is no zoom. When instead we are here and A is equal to 1 and B is equal to 0, we have the sum which is equal to 1 and the carry is equal to 0. So 1, 0, 0, 1, which is correct. Let's go to the other way. 0, 0, 0, 1, 0, 0, 1, 0, correct. 0, 0, 0, 0, 0. Okay, so it is correct. So the simulation is correct. And so we can close this guy. We can close the... Okay. Before you start rampaging in the comments, I know you should open Model Sim. Let me show you. You should open Model Sim in your PC, and you should verify everything with Model Sim. It is true, but now I don't want, because I am bored, so I don't want to waste my time in simulating everything with if the circuit is big, okay, you can use model but if the circuit is simple, go directly with Quartus. This is my advice. So let's open a new file. Let's VHDL file, and let's use again the same, basically the same. Okay, the FullAdder, if you remember, is done in this way. Okay, so we needed to use two FullAdder and to connect them like this. But now the thing gets a little tricky. Okay, a little bit tricky, because when you use VHDL and you use these components here, you have to use a syntax called component. You use the syntax component and you perform the mapping. I will show how I will show how to perform the mapping. So the entity name is this time is FullAdder, and I will use the image of, I will use the spice simulation of the FullAdder, because yes, why not? So in the entity, now you have understood that in the entity you need just to define what is outside the box. In this case, as an input we have sin, A and B. As an output we have the sum and the carry, as we expect it to be. And so let's define A and B, okay, A and B and sin as the input, the sum and the carry as the output. I just wanted to change the names because I don't want to get confused in the port map. So we will call it x1 in1 in2 sin. This will be sum and this will be carry. Okay. Now, inside the architecture of the FullAdder, we need to define the component. Before the begin, we need to define the component. The component of the FullAdder. So component, we call the component FullAdder is, and we copy and component naturally, and inside the component we copy exactly what is inside the entity of the FullAdder. So you basically you use the block that you defined before. So the component FullAdder is port A and B, C exactly as we defined the FullAdder before. Now for the mapping, before using the mapping, we need some signals. The signals are these wires that I'm drawing in red. As you can see, these wires connect something which is inside your box, and this connection here can't be done with the entity, because the entity connects what is outside the box, the signal what is inside the box. So to define this connection here, we need to define a signal. Okay, we need to define the signal, and the signal has to be of the same type. Naturally as the entity that as the input output entity that you are defining. So we will use the signal, the statement signal. Let me skip just signal. Let me use the signal x, y, z as type standard logic. We need x, y, z, w as type standard logic. Okay. And now inside the after the signal, we need to use the port map statement. So inside the begin, we will write HA, which stands for FullAdder. So HA FullAdder port map, And now, at each signal, at each port, we will assign, at each input output, we will assign a signal. So let's do this. FullAdder port map. We can make directly the statement, or we can make the statement with the greater or equal, or we can just write directly inside the parentheses. So basically, I can do two types of port map. I can do x greater than a, y greater or equal than b. This is not greater or equal, it's just an assignment. Or I can write directly port map a, b, c. What is the difference? The difference that this is more clear, because you are saying what kind of input you are assigning to the signal, and this instead takes for granted that you are assigning the first input to this signal here, the second to this, and the third to this, and so on, as you prefer. I prefer this version here because it is more clear, in my opinion, but it is more susceptible to mistakes. So we need to connect the carry. So let's name the signals. This will be the signal X. This will be the signal Y. So we needed to say that the sum of the first alpha, this is FullAdder 1, and this is FullAdder 2. We need to say that the sum of the first FullAdder is equal to X, and the second input is also equal to X. So in this way, they are connected. So in the port map, we will write A to A. This is the first FullAdder 1 and FullAdder 2, sorry. So, in the FullAdder 1, this is A, and this is B. This is X, and this is Y. So A equal to A. Let me write directly A and B. A and B. Then the carry, the sum. I wrote the sum first. So the sum to X and the carry to Y. A, B, X, Y. The second FullAdder receives X in the second input. So the first input we will call this W. Or just C. And I think that you can directly. I think that you can directly call scene like this. If not, we will use W instead. then X, then the sum goes to Y, goes to another, the sum goes to the sum, so let's write sum, and the carry goes to another signal, which call this one V. Okay. So now the sum is equal to sum. We need to define let's define another signal called O for the sum, and the sum is equal to O. I think that it should be the same, but so this signal is O, and then we make the assignment. So we gave a signal to everything basically, and so the carry will be Y or W. So the carry will be Y or W. Let's save this file, save as FullAdder, and now let's use this as top level entity and run the simulation. Okay, I probably forgot. Yes, I forgot these two guys here. Let's wait a bit. Okay, so let's see then the RTL viewer, and let's compare it with this guy here. Oh, it seems that I forgot to. It seems that I forgot to to connect these two guys here. Always check the RTL, because you may forgot, of course, to connect like I did. Okay, this is embarrassing. Now let me check why I did forgot to connect. Because I used the signal A and B, but I forgot to assign A and B. I basically can say in 1 and in 2. Okay, without so you can do both of things. You can call these two signals A and B like I did, or you can directly assign to what is outside, okay, without wasting any time. Naturally, I did this mistake on purpose, because always check the RTL viewer, okay? You may never know what is going on, so before running the simulation, always check the RTL viewer. And now, naturally, it should work. Because this guy will not tell you if you are not connecting something. So always check the RTL viewer. And now you can see that is correct. I have in 1, in 2 inside here. The sum goes inside B, the C goes inside A, the sum is the sum, and the carry is in output with this. So by schematic, I dare say that is correct. You can go inside the FullAdder and see how it is made, like this. You can zoom in and out and in, as you prefer, and this will be a good thumbnail. So let's close the video by running the simulation of VWF. Let me instead node bus, node finder, list, and it will import all the entity that I defined. Let's do the OK. Let's zoom a little bit, and of course let's select this as the worst case possible. So let's put this guy. Oh, why we put the carry? Okay, the sum as first. So let's put this as all 1. These 2 as 1. And now these 2 as 1. Let's run the simulation. Yes, 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 save. Yes, 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 yes. Yes, 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 yes. Okay. So when everything is 1, it is correct that is 1. Yes, because the scene is 1. When scene and in 1 is 1, the sum... Let me test the condition in which... Okay. Yes, when in 1 is 0 and in 2 is 1, the sum is 1 and carry is 0. When these 2 are 1, the sum is 0 and the carry is 1, so it is correct. When these 2 are 1, 0, 0, 1, 0, sum 1 and carry 0. Okay, so it is correct. Thank you for your attention, guys. I hope that you appreciate this video, and see you in the next one.